So in this video, we're going to minimize the length of a line segment or a distance using calculus. So the problem says find the points on the graph of f of x equals 4 minus x squared that are closest to the point 0, 2. So here's the point 0, 2 on the y-axis, and we want to find the generic points x, y on the graph of the parabola 4 minus x squared that are closest to the point 0, 2. So I'm going to start this one a little bit backwards by thinking about what a reasonable, feasible domain would be. And the idea is, from this point, we could move points down this leg of the parabola. And what we want to notice is that the further down the parabola we move, whether it's this direction or over in this direction, the further down we move, the longer the distance will be from the point 0, 2 to the graph of the parabola. That's the first thing I want to notice. So to establish a reasonable, feasible domain, I just kind of want to look at what's a worst case scenario. So just thinking graphically about things, if I pick the points here where we let x run from the closed interval from -2 to 2, and I think about the length of the line segment from there to there, and from there to there, I can visually identify that there's going to be a lot of other line segments that have a shorter length than that. And certainly if I let x roam outside of this interval, I'll just be getting increasingly long line segments. So the first thing I would say is we can establish a reasonable, feasible domain saying the shortest distance from the point 0, 2 to a point on the graph is going to occur someplace between -2 and 2, including plus or minus 2 as possible inputs. So that constructs a feasible domain that's closed over which my distance formula, when I do it, is going to be continuous. So I'm going to be able to use the extreme value theorem to help me in the solution process for this problem. So it says find the points on the graph 4 minus x squared that are closest to the point 0, 2. So if I'm thinking about this, I'm really asking to minimize the length of the line segment from the point 0, 2 to any point x, y on the graph. I'm trying to minimize this distance because minimizing that distance is what it means to be closest from this point to the point 0, 2. So I'm going to give this distance a name. I'm going to call it big D. And then what we want to recognize is from pre-calculus that we know the Pythagorean theorem can be applied to any line segment. So we know that the square of that distance d from pre-calculus is just, from the Pythagorean theorem, going to equal the sum of the squares of the differences between the y coordinates. So y minus 2, the difference between the y coordinates squared, and the difference between the x coordinates squared. So it's going to be x minus 0 squared. That would give us the square of that distance. And I could simplify this down just a hair to get x squared plus y minus 2 quantity squared. Now the length of this line segment d would actually be gotten by taking the square root of both sides of this relationship and taking the positive square root. So the distance we're trying to minimize, big D, is the square root of x squared plus y minus 2 quantity squared. What we want to recognize, however, to make our life easier so we don't have to deal with the square root here, is that if we make d squared as small as we possibly can, that will guarantee that the square root of d squared is small. So if we minimize this, we minimize the square root of that as well. So minimizing the stuff on the inside of the square root minimizes d. So I'm not going to worry about minimizing d. What I'm going to say is let's minimize d squared, which minimizes d as well. Make d squared as small as you can, then the square root of d squared will be as small as it can be. So let's give d squared a name. Let's call it h. H equals d squared. So h is equal to this stuff right here. So the next thing I want to recognize is that I have a function of two variables. H, which is d squared, is a function of both x and y. And I am working with single variable calculus, so I need to find a way to write this as a function of a single variable. What I want to recognize is that my ordered pairs x, y right here, my ordered pairs, can be rewritten as x comma, right here I have f of x equals 4 minus x squared. So remember, an ordered pair x, y is the same as the ordered pair x, f of x. In other words, y is just a synonym for f of x. So my ordered pairs can be rewritten as input x, output 4 minus x squared. I don't have to represent the output with y. I can physically write the equation in. So y can be replaced with 4 minus x squared. So the y right here can be replaced with, we have x squared plus y, but y is the same as 4 minus x squared. So I get 4 minus x squared minus the 2, all squared. And then I can simplify that a little bit. X squared plus parentheses, 4 minus 2 is 2. I get 2 minus x squared quantity squared. And now I have h, which is d squared, as a function of x, and minimizing h will minimize d as well. So the key is that minimizing h minimizes d, because h is the stuff, there should be a squaring on that, h is the stuff on the inside of d. So making h as small as we can will make d as small as we can. Okay, so we want to go and collect our test numbers. So we need critical numbers, and by the extreme value theorem, we need the endpoints on our closed interval. So our test numbers, using the extreme value theorem, are going to be plus or minus 2. And then remember, we find other test numbers by taking and finding the derivative of what we're trying to minimize. So because minimizing h minimizes d, we're trying to minimize h. So we're going to take the derivative of h. So h prime is equal to 2 times x plus, here I have a function composition, so I'm going to use the chain rule, bring the 2 down, 2 times 2 minus x squared, reduce the exponent by 1 to get the first power here, times the derivative of the inside function, which is negative 2x. And I'm going to simplify this a little bit. I see that 2x shows up in both terms, and I see the minus here. Can change that to a plusy. So factoring a 2x out front, I'll get a 1 left, minus 2 times minus 2 times 2 is minus 4, minus 2 times minus x squared is plus x squared. And then this looks like this simplifies a little bit to, that should be minus plus 2 times x squared is 2x squared. And then this is going to be 2x times 1 minus 4 is negative 3 plus 2x squared. So I'm really going to get a 2x squared minus 3 sitting inside the parentheses. And then remember to find the critical numbers for our function, the place where local min and local max might happen. We need to either find places where the derivative is undefined, but this derivative is just a polynomial, so it's defined everywhere. Or we need to find places where the derivative is equal to 0. That gives us critical numbers on our function. So I'm going to set my derivative equal to 0. So the only way for this derivative to equal 0 is either for x to equal 0, or by the zero product property, the other factor, 2x squared minus 3. 2x squared minus 3 needs to equal 0. So now I get a critical number, x equals 0. And then solving this, I'm going to get x squared equals 3/2 by algebra. So x is going to equal plus or minus the square root of 3/2. So there's my other critical numbers, plus or minus the square root of 3/2. So the extreme value theorem says that because my function h right here is clearly continuous on the closed interval from -2 to 2, that I'm guaranteed that there's a minimum and maximum function value for h on this closed interval. And it either occurs at the function endpoints or at the critical numbers. So now it's just a matter of plugging in the critical numbers to determine which of them minimizes h, because the value of x that minimizes h will minimize the distance d between the 2 points. So now I'm going to grab my h. I'm going to evaluate h at plus or minus 2. And I can plug plus or minus 2 in because the squaring is going to kill the negative. So h at plus or minus 2 is going to be plus or minus 2 squared plus parentheses 2 minus x squared. So 2 minus plus or minus 2 squared, all squared, is going to equal 4 from here. Plus or minus 2 squared is a 4, plus 2 minus plus or minus 2 squared is going to be 4, so it's going to be 2 minus 4 but squared. So I get 4 plus 2 minus 4 is -2. -2 squared is 4. 4 plus 4 is 8. So when I evaluate h at plus or minus 2, I get 8. Now evaluate h at 0, the other critical number. So h of 0 is going to be equal to 0 squared plus 2 minus 0 squared, all squared, equals, so I get 0 plus 2 minus 0 squared is 2. 2 squared is 4. I get 4. And finally, I want to plug in plus or minus the square root of 3. So h evaluated at plus or minus the square root of 3 halves equals plus or minus the square root of 3 halves, quantity squared, plus 2 minus plus or minus the square root of 3 halves, squared, all squared, and then simplify. Plus or minus squared will just be positive. Squaring the square root will just give us a 3 halves, plus 2 minus plus or minus squared will just be a positive, and the square root of 3 halves squared is just 3 halves, and this is all squared. So 2 is the same as 4 fourths, so we get 4 minus 3. I should be going for a half there. Let's see. Plus, no, 2 minus, let's do this right. 2 minus, squaring the square root gives us 3 halves, so this is going to be 4 halves. So I'm going to get a half in there, and then squaring the half is going to give me a quarter. So I'm going to get 3 halves plus a quarter, which is just going to be equal to, what's that going to be, 7 fourths? So 7 fourths, when we look at it, 7 fourths is definitely the smallest of 7 fourths, 4, and 8. So plus or minus the square root of 3 halves generated the smallest value of h possible. And because h is the number under the square root sign, that generates the smallest distance possible. So plus or minus 3 halves minimizes the distance d from the point xy to 0, 2. So we want to note that plus or minus the square root of 3 halves minimizes d, the distance from the function to the point 0, 2. Now notice where it says find the points on the graph. I've only found the x-coordinates of the points on the graph, but the points occur in xy ordered pairs. So I also need to get the value of y that goes with the input x equals plus or minus the square root of 3 halves, right? This is the x-coordinate. I need the y-coordinate that goes with it, but remember the function value is the y-coordinate. So we just need to plug into our function f of x, we need to plug in the plus or minus the square root of 3 halves. So doing that, we're going to get 4 minus plus or minus the square root of 3 halves squared equals 4 minus plus or minus squared is just a positive, and squaring the square root just gives us a 3/2. So this is going to be the same thing as 8/2 minus 3/2 is just going to be 5/2. So the points on the graph, the points that minimize the distance D are given by, there's 2 points. They're located at plus or minus the square root of 3/2, comma, 5/2.